In this video, we're going to talk about the octet rule and how to break it. So octet rule is a quick name for talking about the number of electrons we expect in any of our structures. So when we have methane or ammonia or water or carbon dioxide, the octet rule refers to the fact that if you've got 4 orbitals around your atom, you can fill up to 8 electrons into it. So octet, oct for 8. Whether lone pairs on the atom or shared in a bond, to fill the S and P's, you need 8 electrons. And so there are really 2 electrons in each of these bonds. So as far as carbon is concerned, it says, hey, I've got 2, 4, 6, there's 8 electrons around me. Carbon has its octet. Hydrogen really only wants 2 because, well, remember, hydrogen only has the 1s. There's no 2s or there's no 1p orbitals to fill. So carbon has its octet. We go look at nitrogen here. Well, 2 electrons, 2 electrons, 4 electrons, 6 electrons, and its lone pair makes for 8. Oxygen, 2, 4, 6, 8. Over here, well, the double bond, each bond is 2, so 2, 4, 6, 8. That carbon sees 8 electrons, but the oxygens also see 2, 4, 6, 8. And this oxygen over on the right sees 2, 4, 6, 8. In order to have paired all your unpaired electrons, you will have 8 electrons around you in a Lewis structure. This is true for things in the upper right of the periodic table. The carbon, the nitrogen, the oxygen, the fluorine, these will always be obeying their octet rule in all but the weirdest exceptions. There are very, very rare exceptions to the octet rule. But boron is one of them. We saw that in the guided practice video. Boron, because it only has 3 valence electrons, when you pair it with things like chlorine or fluorine or hydrogen, it makes 3 and then it's done. It has an empty orbital. Boron is just an odd element. It's really the only one that does this, but it sits right on the edge of being covalent. It's not strong enough to really attract electrons and go all the way to filling its valence, but it's too strong to lose them all and go to just being a cation. And so it will share electrons, but it doesn't really pull in enough to have a full octet. It's possible if you bring up some kind of Cl-, it can loan its whole lone pair to boron and end up with a negative charge on the boron, and BCl4- or BF4- or various types of things actually do exist. They're just not very stable. So boron's a little bit of exception to the octet rule. But everything else in that second period is going to obey it aggressively. This is not true for the third period or anything else below it. The vast majority of organic molecules are made out of row 2 elements. Most of life is carbon, nitrogen, oxygen, and hydrogen. But we do make molecules out of third and later rows, and these have some octet rule exceptions. If we think about SF2, SF4, and SF6, sulfur difluoride, sulfur tetrafluoride, sulfur hexafluoride. Try and do the Lewis structure. Sulfur with 6, fluorine with 7, just really one that's unpaired. So for shorthand, I'm just going to draw the one unpaired. Know that we've got the other ones on fluorine, but this will make our drawings a lot faster. SF2 works just fine. We pair them and sulfur looks like it has an octet. It says, hey, 2, 4, 6, 8 around my sulfur. If we try to do that for SF4, 1, 2, 3, 4, 5, 6, put our fluorines with the one unpaired. Again, they really do have the other lone pairs. We're just not drawing them for simplicity's sake. Problem is, well, we pair the unpaired and sulfur's out of unpaired electrons. It can't bond to those other two fluorines. So how do we make SF4? Well, sulfur has access to d orbitals. Even though they're not used for a while, we'd fill the 4s before we fill the 3ds, they do exist. And atoms that have those orbitals, in effect, you have your 4 regions. Sulfur can break one of its regions into 2. By using a d orbital, instead of just having the 4 orbitals from the s and the 3 p's, you now have 1 s, 3 p's, and 1 d. In doing so, you open up a new region. There are 5 regions around sulfur if it needs it. The net effect is these electrons unpair and then can be bonded with. Sulfur then has 1 lone pair still there and 4 fluorines. If we do SF6, sulfur has its 6 electrons. We get 6 fluorines. We pair the unpaired. We've run out of unpaired, so we can use 1 d orbital to split this bottom pair to allow those bottom fluorines to attach. And, well, there's more than 1 d orbital, so we can use a second d orbital and dump one of these pairs of electrons into that second d orbital. The result is we break up the other lone pair on sulfur, freeing them to be bonded to fluorines. And that result is we end up with a sulfur with 6 fluorines and no lone pairs. Well, if we go and look at the octet rule for these last two, sulfur sees 2, 4, 6, 8, 10 for sulfur tetrafluoride, and it sees 2, 4, 6, 8, 10, 12 for sulfur hexafluoride. It has exceeded its octet, but it can do this because it has more than 4 orbitals to access. The octet rule is really about only having 4 orbitals, and that's really just for period 2. Happens to be the vast majority of molecules we make, but it's really just those elements that are trapped. You cannot exceed the octet for period 2, but you can, if needed, exceed it for period 3 or later. So let's give a practice. PCl3 versus PCl5. See if you can draw those two Lewis structures. If you're back, well, phosphorus is like nitrogen, so it's going to be 5 valence electrons. Our chlorines, really they have 7, but there's only the one unpaired, so I'm just going to draw the one unpaired to make our life quicker. Well, over here for PCl5, I have a few more chlorines. For PCl3, I pair unpaired, and I'm done. There's no extra atoms, no need to break up lone pairs. I check 2, 4, 6, 8 electrons around that phosphorus. Well, if I pair the unpaired on PCl5, I run out of ways to connect my phosphorus. I can break up that lone pair, turning them into unpaired electrons that can then bond to those chlorines. 2, 4, 6, 8, 10. PCl5 has to exceed the octet to form. We can definitely do this with phosphorus. We cannot do this with nitrogen. Nitrogen might be in the same column, but it's in the second period. You cannot make NCl5, but you can make NCl3. So these are a few examples on exceeding the octet, when our later elements can make more bonds than we would expect from our general Lewis structure rules.